right, so warning, this is going to be a very math-intensive talk. And I'll be talking about the power and potential of custom hardware. And I think a famous example of that everyone's seen is Bitcoin's network hash rate. So back when Bitcoin began, the hash rate was, somewhere between 1 and 10 million hashes per second. Now it's 300 exahash. So it's a huge increase. It's just mind-boggling, really. It's increased by a factor of 100 trillion, 10 to the power of 14.
It seems linear also on a logarithm scale.
And I've since I got into Bitcoin, I've always found mining fascinating. It's just so neat to see the innovation people did as early as 2011 with these custom FPGA Bitcoin miners at a home setup. Just driven by that profit motive to get more coin. And obviously, nowadays we have these huge industrial mines. This one's the Riot Blockchain Industrial Asic Mining Farm in Texas. Just an enormous amount of money and innovation went into creating this. It's not just that the hash rate has increased, the energy efficiency of the chips that are doing the hash rate have also increased dramatically. So the person who wrote the Bitcoin IT wiki, he estimated the original Bitcoin D miner had an efficiency of about 33,000 nanojoules per hash. So every hash costs about 33,000 nanojoules. An Antminer S19 that came out a couple years ago, 0.025 nanojoules per hash. So, about 1 million times improvement in energy efficiency. So what I think is really interesting about Nexa is the proof of work we're using for mining is also it requires a calculation needed to do signature verifications. So if we see even close to the amount of innovation that happened with SHA-256 mining, we will have enormous improvements in the ability to verify digital signatures. Okay, so what might custom hardware for digital signature verification look like? So first we need to dig into the math to answer that question. So this is where we get into that. So I'm curious, has anyone here actually, from scratch, coded the signature sign and verify?
No.
It's actually not that hard to do. So we're kind of gonna.
I've gone through the math. I haven't coded it up.
Okay. So this is the math for our signature. This is from Wikipedia. The one for Nexta is slightly different than this, but I learned that after I made the slide. I didn't want to remake the slide. But it looks pretty easy. You pick a random number between 1 and this big number n. You do what appears to be this multiplication here. You do some hashing. You do some more multiplication. Blah blah blah. Doesn't look that bad. But when you go to implement this, the first thing you're going to realize is this G is not a number. It's this thing called a curve point on this elliptic curve called SECP256K1. And G has an X coordinate by this big huge hex number and a Y coordinate this big huge hex number. So in order to code that, we have to learn how to multiply a curve point by some number K. So this brings us into elliptic curve math. And the addition of curve points on the addition of 2 points on an elliptic curve is defined by this diagram. So if I add P plus Q, basically I draw a straight line through P and Q, and I find where that intersects the curve a third time, and then I go look at the reflection in the y-axis, and there's my point R. So P plus Q equals R. So why is addition that way? It seems kind of weird. The reason addition is defined that way is just because it works. If you it forms what's called an abelian group, and it means you can perform arithmetic on those curve points like you would perform arithmetic on a number. So if I have 3 points A plus B plus C, A plus B plus C equals C plus B plus A.
Okay.
Which, if you imagine different curves, they won't all have that property. So it's kind of weird that this curve does have that property. Okay, so multiplication is just defined as repeated addition. If I want to go 10 times P, well, I just add P to itself 10 times. That's obviously very slow for large N. So there's this thing called this double and add algorithm where you can calculate P instead of in O(n) times in O log n time. So if I want to calculate 10P, I would just do this. First thing I would do is I would double P, then I would double it again to get 4P, then I would add P to get 5P, then I double that again to get 10P.
Okay.
So it allows me to multiply a curve point by a 256-bit number in no more than 256 steps, basically. Okay. And that works because if we know how to add, we also know how to double, because 2P is just P plus P. Okay, so these are the equations for adding curve points. So if I want to add P plus Q, I basically break it down into its X and Y coordinates, and then I calculate the R coordinates using this equation here, where this lambda is equal to all this. You don't really need to worry about the details of that formula. We just want to look, can we code this in Python? So it doesn't look too bad. We basically go through all this in Python. It all works reasonably well until we get our second out. The second out, though, is Python cannot perform modular inversion natively. Because this step here, calculating lambda, requires inverting this number. But this is an integer. The inverse of an integer is like in normal numbers, that would be like some fraction.
Yeah.
But the modular inverse is another integer. So if you try to do that on Python, it just fails. It can't do it. So there's a trick for inverting numbers modulo a large prime, and it's called Fermat's little theorem. So what Fermat noticed was if you have any integer a raised to the power of some prime number p, that modulo that same prime, it equals a. So we can do a bit of algebra. So I multiply both sides by a to the power of minus 2, and I get the identity that a to the p minus 2 equals a inverse. So what this means is we can calculate the modular inverse of any integer by multiplying itself by itself p minus 2 times, and we solve the inverse problem. So I can write an inverse function in Python. I just return the modular pal of a raised to itself p minus 2 times mod p. The next uh-oh is that p minus 2 is a huge number. For Bitcoin, p minus 2 is 2 to the power of 256 minus 979. So it's not practical to go a times a times a times a 2 to 256 times. But fortunately, just like for repeated addition, where I was going P plus P plus P, I did the double and add algorithm instead. There's an algorithm for this that's called the multiply and square. So it'll look like this. So don't worry too much about the details, but the point is you can multiply p by itself a huge number of times in O log n time rather than O n time. Again, the important point here is that modular inversion is expensive. Okay, so now that we've gone through that, we can finally code the elliptical curve point multiplication in Python. So this is our add function, we already talked about. This is my modular inverse function, I already talked about. This is the modular pal function, and this is my double and add multiply function for elliptic curve points. And this works. So now I can take that and I can code my Schnorr signature verification just like this. It's actually super simple once we have those couple functions written. Now if I time this on my laptop, what I get is for this SHA-256 step here, takes 0.01 milliseconds. The add step here takes 0.22 milliseconds. The multiply step here takes 170 milliseconds. So the point here is that elliptic curve point multiplication is far and away the bottleneck for digital signature verification. And that makes sense because each multiplication is going to be about 384 curve point additions. Each curve point addition requires one modular inversion, and each modular inversion is about 384 big num modular multiplications. Does that make sense? 384 being 256, because you got to do 256 doubles plus, on average, 128 adds, if the bits are 0, 1 equal. Okay, so therefore each elliptic curve point multiplication takes about 150,000 big num modular multiplications.
It doesn't get any easier.
You don't even have to think about the equations here. So what crypto libraries do to speed up elliptic curve point multiplications is they don't use those formulas I showed you there. What they do is a coordinate transformation to what's called Jacobian coordinates. So instead of just having the x and y coordinate of the point, they introduce a third coordinate called z. And the whole point of z is to move this denominator, to keep track of the denominator separately as its own variable. And if you can rework the math and come up with equations for elliptic curve point addition and elliptic curve point doubling that no longer involves modular inversion. So if you write a new add function, so this was our original add function that we got, we'll get a new add function like this, which has, so again, don't worry about what it actually says. The point is that this, we've traded off, we've removed the inversion for a bit more multiplication. But inversion is vastly more expensive than multiplication. Okay, so if I replace the original add function with this new add function and I time it, well, these times stay the same because they didn't change, but my multiplication step reduced from 170 milliseconds to 5.7 milliseconds. So 30 times faster. And this is, so that's what like Peter Woolley's library does. It uses that coordinate transformation. Okay, so now let's look at how many big num modular multiplications per elliptic curve point multiplications are required. So in the best coordinate system I can find, point doubling requires about 8 big num modular multiplications. Point addition requires about 11 big num modular multiplications. If we're multiplying a curve point by some random number, like a 256-bit number, it's always a 256-bit number. On average, we're going to have about 256 doublings and 128 point additions, assuming the ones and zeros are balanced. So that allows me to calculate that there's about 3,472 big num modular multiplications per curve point multiplication. And then finally, there's 2 modular inversions to convert back to your regular xy coordinates, which adds another 768 big num modular multiplications. So in total, you have about 4,240 big num modular multiplications, which is a lot better than the 130,000. So converting to the Jacobian coordinates is definitely worthwhile. Okay. So the point I want to make here is that for signature verifications, big num modular multiplication is a critical operation. If you can do that fast, you can do everything fast. So now let's look at building a fast big num modular multiplier. First, I want to consider just the big num multiplication part without the modular reduction. So here I'm going to multiply 6 times 13. So I write 13 out in binary, and I write 6 out in binary. So the first thing I'm going to do is just what you learn in school. 0 times 1 is 0, 0 times 0 is 0. That's all zeros. Then I go to this number. 1 times 1 is 1, 1 times 0 is 0, and so on and so forth. And then I sum up these columns, and I get this answer here, which in binary is 78, which you can confirm is in fact 13 times 6. If I put this into equation forms, more general forms, where A and B are the binary digits, it follows this equation here. So we can perform multiplication in hardware the same way we would perform multiplication on paper. And we can perform that in a simple step using the hardware called a fast multiplier. In order to do that, we need 2 circuits. We need a 1 by 1 bit multiplier, and we need something called a full adder. A 1 by 1 bit multiplier is just an AND gate. So if I want to multiply 2 bits, A and B, I just pass them through an AND gate and I get the product. And that should be pretty obvious from the truth table. If either of the bits are 0, the product is 0. If both bits are 1, the product is 1. An AND gate is built with 6 transistors. So this, on an Asic, implements that function. The next thing we need is a full adder. A full adder takes 3 input bits, A, B, and this carry in, and gives us a sum. So if you forget about the carry in for a sec, if A is 0 and B is 1, the sum is 1. If A is 1 and B is 1, the sum, well, it'll be 0, and the carry out will be 1. So 1, 0 is 2. If the carry in is 1, well, that just adds 1 to all this. So if the carry in is 1, and these are 1, then the answer is 3. So this will be 1, and that'll be 1. So these are the 2 building blocks we need to make our hardware multiplier. And this, in terms of gates, looks like this. I won't explain why, but it's easy to prove to yourself that that does, in fact, add those numbers. And this circuit here is built using 30 transistors. Okay, so now let's look at actually creating an ASIC for our single cycle hardware multiplier. So I've drawn the diagrams, so it's basically exactly this. So I want to multiply this binary number times this binary number, and you'll notice I'm using the same notation here. So A0, B0, A0, B0, that's just an AND gate. A1, B0, A1, B0, A0, B1, A0, B1. So I'm multiplying those 2 bits, and then I'm summing it, putting it in here. And you can kind of follow through, and you'll see that this hardware is performing exactly what you would do with pen and paper if you were multiplying these 2 numbers. And what's cool is this will compute the product in no clock cycles. You put the bits in, and you get the bits out as soon as that electrical signal is propagated through the circuit. Now, obviously, we can scale this. We can stretch this to 256 bits, and this product to 256 bits, and we'll get this huge big multiplier circuit that multiplies 2 large numbers in 1 clock cycle. If you kind of analyze this bit, you'll realize that such a circuit would contain n squared AND gates, so for 256 squared AND gates, and n times n minus 1 full adders. So now we can calculate how many transistors our ASIC will have that performs this multiplication. So for 256 by 256, I get 256 squared times 6 for 6 transistors per AND gate, plus 256 times 255 times 30 for 30 transistors per full adder. Gives me about 2.4 million transistors in my single cycle hardware multiplier, which seems like a big number, but in the world of ASICs, it's not. Like modern processors will have billions of transistors. So I've done the hardware multiplication. Now I've got to do the reduction. The modular reduction is actually really easy in Bitcoin because we're taking the modular reduction with respect to this prime number p, which is very close to 2 to the power of 256. And Satoshi chose that for a reason, because it makes the math very fast. So I've already overloaded with the math, so I won't explain why it works. But there is a trick for reducing modulo what's called a pseudo-machine prime. So a prime number that's almost the power of 2 to the n. So the way it would work is you'd put your 2 numbers through the multiplier, you get a 523 or a big result. And then you can reduce this all using this formula to get your answer modulo that prime. And again, this will operate instantly. Well, not instantly, but with no clock cycle. So you put your input in here, and you'll get your modular reduction out in a very short amount of time. Okay, and the point I want to make here is, if you actually analyze how many transistors are in this circuit, it's significantly less than in the multiplier circuit. So for energy consumption and transistor count, it's that big 256 by 256 multiplier that's consuming all the energy and taking all the transistors. Okay, so we can look at energy consumption. So in total, our circuit has about 2.9 million transistors. If you look at data for how much energy is dissipated each time a bit on a transistor switches states, at the 28 nanometer process, it's around 0.1 femtojoules, or 24,000 times the thermal energy. That doesn't mean much, but it will. So assuming about half the gates change state per multiplication, it works out to about 0.145 nanojoules per big num multiplication and the modular reduction. But we have to do that 4,240 times to do our curve point multiplication, which works out to about 0.6 microjoules. We need 2 multiplications per strong signature verification, so I get about 1.2 microjoules per verification, which, let's translate the numbers that make sense. So if you wanted to verify 1 million transactions per second, that would take about 1.2 watts, which is nothing.
Right, sounds pretty good.
1 million transactions a second. Wow.
So I was just interested in what the actual theoretical bound is. And as we get to smaller and smaller processes, so as you go from a 28 nanometer process to like a 7 nanometer process, which some things are being built with, or even a 5 nanometer process, this energy per bit flip gets significantly less. Eventually we'll reach like what are called the physical thermal limits, which is about 6 times Boltzmann's constant times temperature, 6 times the thermal energy. So we still have about a 4,000 improvement, according to laws of physics, below this before we actually encounter the fundamental limits of physics here. Okay, so we actually built a working elliptic curve point multiplier using an Intel DE1 Cyclone B FPGA. So I have the report here from my students. Anyone wants to look at it?
Was that a commercial requirement project? Was that a commercial project or a...
No, this is I went to UBC and I did the engineering physics program. So I still interact with them. So once in a while I'll sponsor projects. So I sponsored this project and this great group of students did it. And they did a really great job. So they got it working. And so the multiplier that they built consumed 754,000 NAND gates. So when they actually put that on the FPGA, it tells you how many NAND gates equivalents it's consuming. So that worked out to about 3.5 million. We estimated 2.9 million, so our estimates were on the right track to what we empirically verified. They were able to run that at 50 megahertz and perform single cycle big num multiply and single cycle modular reduce. Their throughput was 6,713 point multiplications per second. I think they did something wrong with the pipelining because they should have been about 20,000 given that. So I think they just weren't very efficient when they actually wrote the state machine to move things around. And that consumed about 1.5 watts of power. That's a lot worse than 1.5 watts per million. But remember, this is an FPGA, which has a bunch of other baggage along with it. It's like a programmable Asic. On an Asic at a smaller node process is going to be vastly more efficient than that. And their energy worked out to about 0.5 millijoules per verification, so about 500 times worse than I think we could do with an Asic, but still pretty good. Mm-hmm. And they actually won an award for this.
Yay.
And there's a kind of a nice event that's put on every year at the EngFiz Project Fair. So they were all set up to give. We had worked on like a dice talk. They were going to tell an audience of a couple hundred about elliptic curve point math, about Bitcoin and things like that. But that's when COVID hit, so the whole thing was canceled. No. So that was very disappointing for me. So conclusions. Elliptic curve point multiplication is the bottleneck in Schnorr signature verification. Modular inversions are expensive. If you want to do signature verification, you really need to transform to some different coordinate system where you can avoid modular inversions. The critical hardware operation is the 256 by 256 bit multiplication modulo Bitcoin's prime. Approximately 4,240 of those operations are required per curve point multiplication. The multiplier stage is about 5 times more energy intensive than the modular reduction stage. So really, it's that big multiplier that eats up all your power. We built a hardware circuit on an FPGA to perform this operation. On a 28 nanometer ASIC, I estimate it would consume about 0.4 millimeters squared of area. So this is a very tiny chip. So you could put several of these circuits on a single ASIC.
Just trying to figure that out. Did you calculate that? For how many transistors are on ASICs these days?
Like in the billions, right?
Right.
So
So it seems like you could put more than several. It seems like you could put like hundreds of these.
Oh yeah, hundreds, yeah.
Yeah.
In the hundreds, yeah, definitely.
Okay.
So on a 28 nanometer ASIC, you need to connect a couple of these in parallel, but you can comfortably do 1 million Schnorr signatures per second, consuming on the order of 1 watt. Then
per 1 watt per though, right? No.
Well, no, but 1 watt per. It's important to think about watts per signatures as opposed to per circuits, right?
Right.
So you need we haven't calculated how fast the circuits run.
Right.
And probably what you care about is multiplications per joule as opposed to multiplications per second, because you can parallelize it, right?
Right.
So that allows you to reduce your power consumption by putting multiple things in parallel, running all your circuits at a lower voltage and a lower clock rate just to save energy, and then pick up for that by doing things in parallel.
Right.
Where a computer has a different problem because most things are limited by single-threaded bottlenecks.
Right.
So on a computer, it's optimized for single-threaded speed. So they're running at higher voltages, higher clock rates, consuming more energy than if they could do the calculation in parallel in a slower clock and a lower voltage.
Okay.
So Andrew Stone and I were talking about curious how this applies to Nexa. So right now, the Nexa difficulty is 0.35. What that means is the current difficulty divided by the initial difficulty is 0.35. To turn that to a hash rate, I multiply 0.35 by 2 to the power of 32, because I'm basically looking for something with 32 leading zeros. Then I divide it by 120 seconds per block. So I figure the network hash rate is around 12 million hashes per second.
Yeah.
So we're 24 million elliptic curve point multiplications per second. Andrew said his computer can do about 13,000 hashes per second on a laptop. You said 400,000 over.
Yeah, I didn't do that math, but I'm going to trust you.
Okay.
Yeah.
And this makes sense based on the number from Peter Woolley's library and things.
Right.
That's right in line with
Okay.
what I've been.
Yeah, you miners know, it
That's
prints
something
out
right.
every 30 seconds, right?
Yeah,
so
I've
it's doing
got
about
one here.
400,000
I
for
can-
30 seconds.
Yeah, it's
So-
0.013 megahashes, right? Which is roughly what it comes out at.
Okay, great.
Like on a laptop.
Right.
Like my laptop.
Okay, so I figure right now the hash rate's around 2,700 laptop core equivalents.
Right.
So obviously some people are running with 4 cores or something, so the
Yeah,
total
but
number of laptops might be less than that.
A couple hundred laptops.
Yeah.
Physical laptops.
Yeah, so I thought that was kind of cool. And then I also thought it was cool, so that if we were to build such an ASIC, we could double the hash rate, consuming only 12 watts.
Yeah.
So a little thumb drive could overpower the network right now.
Idea.
Yeah, and that's
The
it.
magic of ASICs.
Okay.
Thank you.
Thank you, Peter. It's a really great talk.